concepts today, but the first thing I'd like everybody to do is number 49 individually. So page 250, number 49. Now, I also need you to make some assumptions. The mass is 1 kilogram, the initial velocity is 0, and it's on a frictionless surface. And then I want you to give me the velocity after each impulse. What is the initial velocity of the object?
0.
0. When does it stop being 0?
2 seconds.
At 2 seconds. Okay, so picture you have an object sitting on a frictionless surface, no velocity. Nothing happens for the first 2 seconds. At 2 seconds, we begin to push it with a force of 2 newtons, and then we keep applying that force for 2 seconds, right? So what that means is that we've applied an impulse, right? We change its momentum, and we give it a change in momentum or an impulse equal to 4 newton seconds. Right, so now that object that was sitting motionless on frictionless surface has 4 newton seconds of momentum. Now we know momentum is P equals mv. So if the momentum is 4 and the mass is 1, that means the velocity is 4. Right? So that means that right here in this region, the velocity is 4 meters per second. Now it's equal to the momentum because the mass is 1, right? If the mass wasn't 1, then you'd have to calculate what is the velocity, but we made it simple by making it 1. So now it's moving at 4 meters per second for 2 seconds in here with that much momentum, and the momentum will begin to change at 6 seconds, right? Because that's when we start to push it to the left with a force of -2. And we do that again for 2 seconds. So how much of that 4 newton seconds of momentum do we take away?
All of it.
All of it, right? Because this impulse, change in momentum, is -4 newton seconds. So whatever momentum it had has now been taken away. So what's the velocity then?
0.
At 8 seconds, it's 0, right? You have no momentum. So that means your velocity is 0 at that point. So now it's sitting at rest again. And then at 10 seconds, we begin again by pushing it with a force of -2, but we only do that for a second. So how much momentum do we give it? -2 newton seconds, right? And that means that if its mass is 1 and it has -2 newton seconds of momentum, at this point, it's traveling at -2 meters per second, right? So it's real simple because the mass was 1 and we started from rest.
How did you get 0 the second part?
Because whatever momentum it had, it kept here, but then we took it away.
So why is the next part 0?
So then if you have 0 momentum, 0 equals mass times v, 0 equals 1 times v, v0. Okay, 2 targets, 2 identical arrows. Okay, the mass is 1, we'll say, just to make the number simple. VI is 1. Mass is 1. VI is 1. So what is the initial momentum of each arrow? Anybody? 1, right? 1 kilogram meters per second. So they travel with that momentum towards the target. Now, the first one's going to get stuck in the target. So here it is, it's stuck in the target. What is the final velocity of this arrow? 0. So therefore its final momentum is 0. So what was the change in momentum or the impulse? -1, right? It went from 1 to 0. Now the next arrow, instead of getting stuck in there, bounces off. Right? So this arrow is going to bounce off, which means it reversed direction. Right? It hit and then it changed direction. So that means it's going to have a negative velocity. So maybe we'll make it -0.5. So it bounced off at -0.5. So what is the new momentum of the arrow? What's the momentum of this arrow? Negative 0.5. So what was the change or the impulse for the arrow? It went from 1 to negative 0.5. So that's a change of negative 1.5, right? Kilogram meters per second. So therefore, this had the greater impulse, right? Does everybody see that? This is called rebounding. Probably Ryan, you won't forget that, right?
Oh,
It's called rebounding when it changes direction like that. Requires a greater, or it is a greater momentum change. So if I asked you tomorrow, we have a raindrop and a hailstone of the same mass and both hit your car. The hailstone dents the car, the raindrop doesn't. Why?
the hills and rebounded.
Rebounded, right? Requires more impulse, greater force, more likely to dent your car than a raindrop, okay? Okay. He's going to throw the ball to the catcher, right? So the pitcher is going to apply a force to the ball, right? And it's going to take his arm time to go from back here to where he releases it. So he applies a force through a distance, right? It takes time to do that.
That guy's driving the car.
And when he lets go, the ball then has what? Begins with M. Begins with M.
Momentum.
Momentum. Because it has velocity, it has momentum. So now it's traveling through the air with the momentum the pitcher gave it. Let's say that that's 10 kilogram meters per second of momentum. And it's going to keep that momentum until somebody takes it away. Who takes it away? The catcher, right? So then
Don't worry, catcher, take it.
it comes to the catcher and he takes it away. How much momentum did the catcher take away? All of it, right? So that means he provided the same impulse as the pitcher. Right? Now, so the impulse is the same, right? One gives it, one takes it away. Now, who provides more force? So the catcher, when he catches the ball, Garrett, how far back does the mitt usually go?
What do you mean, like?
Like when he catches it? Hardly at all, right?
Yeah.
He just catches it. So it pretty much stops instantly. So if the ball is stopped with a little time, that means that he had to apply a big old force to it, right? So the force and the time equals 10. The pitcher's applying a little bit of force, but he's doing it through this distance. So that means he's doing a big time. Still equal to 10. So who applied more force? Catcher, right? Because the time was so little. Catcher had to apply more force. Everybody see that? So we have a rifle and a pistol, right? What causes the bullet to go forward is the gases in the barrel expand, right? And they push the bullet out as they expand. Once the bullet reaches the end of the barrel or the pistol, then the gases expand everywhere and they no longer are pushing on the bullet. So if the same force is applied to each one, which one has the force applied longer, Brad? Yeah, right, the rifle. So the time here is greater than the time here because it's in there longer. So if you got a greater impulse on an object of equal mass, then it comes out of here faster, right? Because the force is applied longer.